Number 17, if you read, the problem states show that the height of the cylinder of greatest volume, which can be inscribed in a right circular cone, is 1/3 that of the cone. Okay, so let's draw a cone. This is a cone given to you, and you are cutting out a cylinder from this. You are cutting out a right circular cylinder. Okay, this is the height of the cone. So here, if you see, the cone is given to you. So therefore, um, the volume of the cone must be constant because the cone is given to you. Equal to V, say constant, right? Because the cone is already given to you. Now, if I assume the base radius of the cone to be capital R, if I assume the height of the cone to be capital H, then both H and R are constant because volume is constant. Let H and R be the height and base radius of the given cone. Respectively, right? So here H and R are both constant. Right? Now you want to cut out a cylinder from this cone. So if I assume the base radius of this cylinder to be small r and the height of this cylinder to be small h, let H and R be the height and base radius of the inscribed cylinder. So H and R are constant or variables in this. Are both variables. Right? So now what you see is, if I call this point as A and if I join this, if I call this as point as B and this as C, and if I call this point as say D, and if I call this point as C. Now what you see is that the triangles ABC and ADE are similar. That means their sides are proportional. What side should we take? We obviously neglect the side AC and AE. We neglect these two because we don't need these two sides. We don't need the slant height of the cone. Okay, so we write the other two sides. What are the other two sides? AB by AD is equal to BC by D. Yes. What is AB here? If you see AB this length, what is this length here? Capital H minus small h divided by AD. AD here is small h divided by BC. BC here is small r, radius of the cylinder. and DE is the radius of the cone, right?
Yes, sir.
So now we have got a relation between h and r, small h and small r, which later when we'll be writing the function for the volume of the cylinder, which we need to maximize, then we can, with the help of this equation, we can convert it to a single variable, right? So let us calculate h from here. H is equal to, let's cross multiply first. HR is equal to R times H minus H. That means um, a better way to calculate here is, because H is on both sides, you can write this as, this AD is capital H, not small h. You see in the figure, AD is capital H, right? So that's how. Now you can, if you want to calculate H from here, you can write this as 1 minus H by H is equal to R by R. That means H by H is equal to 1 minus R by R. That means small h in terms of R is capital H, 1 minus R by capital R. Now you forget about the small capital H and capital R because they are constants. What we want to get is the relation between these two variables, which we have already got, right? Capital H and capital R are of no consequence because they are constants. Okay, let us call this 1. Now what we want to do? We want to um, greatest volume. That means cylinder must be of greatest volume. So volume of the cylinder. Let us call this V1 because we have already called the volume of the cone. Volume of the cylinder is pi r square h. That means from 1, small h is equal to h into 1 minus r by r. Let's call this 2. Putting this value in 2, we get V1 is equal to pi r square. And small h, if you put the value, h into 1 minus r by r. Now you can multiply pi r square h throughout for the convenience of differentiation. So you can write this as V1 is equal to pi r square h minus pi r cube h by r. Right. So we now, if you see, this function is down to a single variable r. Right. So we find out dV dV1 dr. dV1 dr is, r is a variable, so pi h into 2r minus pi h by r into differentiation of r cube is 3r square. So what you get here is 2 pi hr minus 3 pi r square h divided by r. This is what you get as dV1 dr. So for maximum or minimum volume, dV1 dr must be equal to 0. That means you get 2 pi hr minus 3 pi r square h by r is equal to 0. Now from this, you can take pi HR common. To get 2 minus 3r by r is equal to 0. That means you get 2 minus 3r by r is equal to 0. That means you get 3r by r is equal to 2. That means you get r, small r, is equal to 2r by 3. Now we have got the variable in terms of a constant, right? So we have actually found out the value of radius of the cylinder. Okay. So now once we have got the radius of the cylinder, at this value, the volume can be maximum or minimum. So how do we check for maximum minimum? Second derivative. Therefore, d2 v1 dr2 is equal to ddr dv1 dr is ddr dv1 dr 2 pi hr minus 3 pi r square h divided by r. Yes, okay. Now from here we can differentiate. You can take 2 pi h common, 2 pi h out because it is a constant, and ddr of r is 1 minus. Now from here you can take 3 pi h by r out, and you can differentiate r square to get 1. Okay, so essentially what you get here, the second derivative is 2 pi h minus 6 pi h r by r. So that now you can take from these two 2 pi h out to get 1 minus 3r by r. Now we want to check the sign of this at r is equal to 2r by 3. d2 v1 dr2 is equal to 2 pi h 1 minus 3 by r into 2r by 3. So this r gets cancelled. So what you get here is 2 pi h into, and this 3 also gets cancelled. So you get 1 minus 2, which is negative, right? So therefore at thus v1 has a local minima, maxima at r is equal to 2r by 3. Right? So volume of the cylinder is maximum when radius is equal to 2/3 the radius of the cone. But here the question is different. Here if you see, the question is, show that the height of the cylinder of greatest volume which can be inscribed in a right circular cone is 1/3 that of the cone. You have to find a relation between, not between the radius of the cylinder and cone, but you have to find a relation between the heights. So if you want to find out the relation between the heights, we can always use this one here from 1. So from 1, h is equal to h 1 minus r by capital R. This was 1. So now put the values, which is equal to capital H into 1 minus the value of r here is 2r by 3 divided by r. So now this r and this r gets cancelled. You simply get h1 minus 2/3, which is equal to h by 3. Right? So we have found a relation between the heights. Hence, volume of the inscribed cylinder is maximum when small h is equal to 1/3 capital H. That is when the height of the cylinder is 1/3 that of the cone. And that finishes this problem. Okay. Can move on to the next question then. Now the next question is, let's see what is the next question. Okay. Next question, number 18. Now 18 is a little long problem. Okay. Let's finish this then, even if it's long. Assuming that the stiffness of a beam of rectangular cross section varies as the breadth and as the cube of the depth, what must be the breadth of the stiffest beam so that which can be cut from a log of diameter A? Now you have a log this way. Okay.
So what
This is a
does
cross
beam?
beam means this kind of a log. This kind of a log, you have to cut a beam from this. Okay.
Hmm.
If you want to
Beam
cut out
means
a
like
beam, that means you
this.
have to cut out a cubical piece of. Understood? You have to cut this out. Yeah.
So what actually is beam?
Beam is you have seen the support uh, support that is given in buildings like pillars. Those are called beams. Beams are
Yes.
like pillars. These are long
Okay.
pieces
Okay.
of cement or pieces of wood. Okay, especially in the old buildings, you will see there are wooden beams.
For supporting the roof, basically, in the old
Exactly,
buildings
for
they used to.
supporting a certain structure, beam is given. Okay, so especially in the old British ones, you will see these wooden beams. Okay, it was cut out from these logs of this was very expensive wood. I don't know whether it is available right now. These were called Burma teak. Okay, these were very expensive and very strong wood. Even if you go to some of the Dalhousie buildings nowadays, the old British offices, you will find stairs made of this teak, this wood piece of wood. They are very strong and
I
very.
have, sir, in my village.
Oh, you have. Okay.
Yes, yes,
And
sir. In
even in
the,
the old Bengali households, the Thakur body types,
Yes, sir. The
you will find some of a little bit of that hint of that old wooden beams and all are there. You'll find these. So that is a question here. Okay, yeah, I have drawn a cross section of this beam here. Okay, I've not drawn the entire beam. I've drawn a cross section of this beam, and from this beam, because I want to cut out a rectangular piece from this log. So that is why I want to cut out here and I want to cut out here. So what I am doing is I'm chipping off these pieces. Okay, I'm taking out these pieces. So I only want a rectangular. So which I'm doing here also. This one. Okay, I'm not drawing, but this is what I want to cut out. Fine. And these were tough. These buildings, they used to be very tough. This piece of wood, uh, it can outpass any cemented structure also. These wooden structures, they were so strong. So Devanjan must be doing this.
Yes, yes.
You have your own house. You must be knowing better.
Yes, it is still standing. I can see.
It is
It
still?
was built nearly
Yes,
40, around 40 years almost past my
40
old
years.
house.
And
In
I'm sure still there is
yes,
no sign of termites or anything on that wood. I'm sure.
yes, sir. Yes.
So that is what you'll see. Anyway, coming back, assuming that the stiffness of a beam of rectangular cross section, so that is why I've drawn this right angle triangle, because of rectangular cross section, varies as the breadth and as the cube of the depth. Let us call this as your breadth, and let us call h as the depth. Okay. Um, so since the beam is given, if I assume the diameter of this beam to be A is constant. So let A be the diameter of the log. So here A is a constant. Fine. Now I say let B and H be the breadth and depth of the rectangular beam respectively. So if B and H are the depth, breadth and depth, that means B and H are variables, right?
Yes.
Fine. So now what you see is that the stiffness of the beam of rectangular cross section varies as the breadth and the cube of the depth. So stiffness varies as breadth and cube of the depth. That means the stiffness, let's call it S, varies as B into D cube. Now you know if you have done variations in class 8, I think I had discussed. And if you remember, if S varies as BD cube, then you can write this as S is equal to some constant times BD cube, right? Even if you have not done variations, just remember that if S, whenever you see this, mostly science students will know that if S varies
Yes,
as
sir.
BD cube, then S
B
is equal to
cube
BD.
to
You
that.
must have done it in physics also last year. Yes.
Yes, sir.
Okay, physics you must have done. So S is equal to BD cube. So the BH cube, in fact, I've taken D, this as H, BH cube. Okay. So where K is called the constant of proportionality. Okay. Now, if you see in this is a right angle triangle here. And in this right angle triangle, what is the relation between AB and H? A square is equal to B square plus H square. So A square is equal to B square plus H square. Okay. So let us call this 1. From this, actually B and H are both variables. This relation will actually help us transform the actual function into a single variable. Okay. Now you see that stiffness is equal to KB cube. Now, if you read the problem, it states that um, the stiffness of the beam, assuming that stiffness of the beam, what must be the breadth of the stiffest beam? Stiffest beam, that means you will have to maximize this, right? So we have S is equal to KBH cube, right? So from 1, because it has two variables, S, you can, with the help of 1, you can convert it to a single variable by writing B is equal to root over of a square minus h square. Putting this, let us call this 2. Putting this value in 2 above, we get S is equal to k h cube root a square minus h square. Now it is down to a single variable h, right? And now we can differentiate this because they have said the stiffest beam. Therefore, we need to maximize S. We need to maximize S. In order to maximize S, we first need to find the first derivative, ds dh. How do you find out ds dh? This k is a constant, you can keep it out, and the rest you can differentiate by u into v formula. H cube is 3h square, and you keep this as it is, root over of a square minus h square, plus, and now you keep h cube here, and you differentiate root over of a square minus h square, which will be 1 by 2 root a square minus h square into differentiation of what is within the radical. So this is minus 2h. Okay, which is equal to k into now from, let's simplify this, then we can 3h square root over of e square minus h square. Now this 2 and this 2 are going to cancel, and there's a minus sign here. We'll combine here to give you minus h to the power of 4 divided by root over of e square minus h square, which is equal to, now you can take out h square also, get kh square into 3 root a square minus h square minus h square by root a square minus h square. And now you can take the LCM. Kh square, you get thrice a square minus h square minus h square divided by root a square minus h square. Okay, so now you can simplify this, the numerator of this, to get 3a square minus 3h square minus h square divided by root a square minus h square, which you ultimately get as kh square times 3a square minus 4h square divided by root over of a square minus h square, right? So this is what you're getting as ds dh. For maximum or minimum stiffness S, the first derivative must vanish. ds dh is equal to 0. So that means kh square into 3a square minus 4h square divided by root over of a square minus h square is equal to 0. That means 3a square minus 4h square. That means the numerator must be 0, isn't it? Kh square into 3a square minus h square is equal to 0. That means 3a square minus 4h square must be equal to 0. That means you can find this out as 4h square is equal to 3a square. Means h square is equal to 3a square by 4. That means h is equal to, because it is positive, so we'll take the positive square root only, 3a square by 4. So you're getting h is equal to a root 3 by 2. So at this height, the stiffness is either, at this depth in fact, the stiffness is either maximum or minimum. Now, how do you find out whether it is maximum or minimum? You will have to find out the second derivative and then check at this height the sign of the second derivative. So let's find out the second derivative. But before finding out the second derivative, we first simplify the first derivative a little so that it is easier for us to differentiate. ds dh, if we had found this out to be kh square into 3a square minus 4h square divided by root over of a square minus h square. This is what we had found out the first derivative to be. You can multiply this throughout to get 3k a square h square minus 4k h to the power of 4 divided by root over of a square minus h square. Right? Now it will be convenient for us to differentiate, because this we can differentiate by u by v rule. So therefore d2s dh2 is equal to ddh of ds dh is equal to ddh of all this 3k a square h square minus 4k h to the power of 4 divided by root over of a square minus h square. Fine. U by v rule. How do you differentiate by u by v rule? V into ddx of u. U here, if you see, is 3k a square h square minus 4k h to the power 4. K is a constant, a is a constant. So you can take 3k a square out and you can differentiate h square to get 2h minus 4k is a constant. You can take it out and you can differentiate h to the power of 4 to get 4h cube, right? Minus u. U here is 3k a square h square minus 4k h to the power of 4. This is u into ddx of the denominator. How do you differentiate the denominator? First differentiate the radical 1 by 2 root a square minus h square, and then you differentiate what is within the denominator, which is minus 2h. This entire thing must be divided by root over of square of the denominator, right? So this is in the next step. What you can do is, if you see, if you multiply, you have a 2 here and you have a 16 here, right? So you can take 2 out. If you take 2 out, you will have to take the LCM also in the next step. So if you take 2 out, you will get 2 root a square minus h square into 3k a square h minus 8kh cube minus, and here this 2 and this 2 will cancel, and this minus sign here will combine with this minus sign to give you a plus sign. So these two will combine to give you a plus sign, and this will become h into 3k square h square minus 4k h to the power of 4 divided by root over of a square minus h square, and this entire thing divided by a square minus h square. Now you take the LCM in the numerator. To get twice a square minus h square into 3k a square h minus 8k h cube plus 8 into 3k a square h square minus 4k h to the power of 4 divided by, and you have a radical a square minus a square that comes down. So you get a square minus h square to the power of 3 by 2. Right? This step okay with you? Okay, so now what are we getting here?
Yes.
We have already got this. Now we will check the sign. Okay. But it seems I don't have time, so I'll stop here. Okay, I've got the expression here, so I'll stop.